Good. Let us continue where I stopped before. But before I do that, please let me correct the statement which I made before, which Matt kindly pointed out. And of course, when mathematicians are in the audience, nothing goes unpunished. No slip. No, but it's very good because in your notes you should have the correct formula, and in fact, indeed, you have to rotate this F0 by the remaining ends in order to get really a mixed Hodge structure. Good. I don't want to lose time on this. It's just a fact that you can check this. Now, where did we left off? We wanted to use the classification, and what we found is that within this classification, when we have these types, which you just can determine by the ranks very nicely, ranks and eigenvalues, then you can check that if you use the Weil-Petersen metric, only the types which are starting at 2 are actually at infinite distance. Yeah. So this is in contrast to the Hodge metric, where everything would be at infinite distance. In the physical metric, only these higher types are at infinite distance. And now what you can do is you can ask, well, can I construct models for these pi's, for these periods, near every boundary for every of these diagrams which I gave? It's quite a task. Yeah. But in fact, this is in reach. This can be done in principle. And we have demonstrated this for 2 moduli examples. And why is this at all in reach? It is in reach because of a fact which Matt explained briefly, but only because of time in short terms. There is in fact another even deeper result than this nilpotent orbit theorem, and this is this Sl2 orbit theorem. Namely, in fact, that when you think about these ends, what you should do is you should think of them as lowering operators in some LH Sl2 algebra. So you should think about them as being part of an Sl2 algebra, which has a lowering operator, which is this n. I put a minus here. Then there's a raising operator. And then there is kind of a level operator. What's the name of such an operator? Weight. Yeah, so which measures the weight of the sum. Yeah. And then these will form an Sl2 triple. So an Sl2 algebra. Now, the tricky part of this is we already introduced the ends, and it's not true that I can just take all of these ends and complete them into Sl2s. I can do that. Very easy. There are many choices. You can do it, but you wouldn't have a huge mess. Why? Because despite the fact that all these ends here commute with each other, if I complete them into an Sl2, these individual Sl2s will not commute with each other in general. And the genius in this theorem of the Sl2 orbit theorem, it actually tells you, well, if you're clever, there is a procedure of how to producing out of these ends, other ends, and minuses, and pluses, and zeros, which are actually forming Sl2s and which all commute. And in order to use them, and then you can even use them to approximate your nilpotent orbit even further. So you have to go further out on the boundary, and then you can use these commuting Sl2s to approximate your nilpotent orbit. And this is really a very remarkable fact, because as soon as you have these commuting Sl2s, everything splits into blocks, Everything is in the SL2 blocks. They don't talk to each other. It's like a gigantic matrix which has just block structures, and you can just individually consider them, and you can study the whole system in generality. So everything turns into SL2 representations here. And then when you look at these diagrams which we have drawn, and you have again to turn your head, depending on where you read them, then you see that all these points which align along these diagonals, they are just SL2 representations. Yeah? So it's just the highest weight react to the end. Lower weight, generate a finite dimensional SL2 representation.
The completion is unique. The completion of this.
Yes, it's remarkable. It's unique in the sense that if I have a given as a nilpotent orbit, I can uniquely determine the SL2 and some other information which I will give in a moment.
But in this strict asymptotic, you're saying I1 is much bigger than I2 and so on. So this means that you have chosen an order.
Exactly.
And then it depends on the order, maybe.
It depends on the order, absolutely. And that's why these diagrams which I draw are so useful. The order corresponds to how you go through the diagram. Yeah, that's the order. You go along this upper path, then this is this order. If I change it, then you go to the other order. And for each of these enhancement chains in the enhancement diagram, there is a different SL2 orbit. And all of them can be computed. Yes.
Yeah, I was going to say, I think it's worth emphasizing that you're starting with these SL2s that don't. Tony Kaplan-Schmidt is giving you SL2s which do commute.
Right. I will
but which SL2s that do commute it gives you depend on the choice of ordering.
Right.
And it's always, if the first one, it leaves alone.
Yes. So this depends on the ordering, and you have to consider all. Yeah. Consider all. And then this is this diagram.
But is the idea that the non-commutation of the SL2 triples is exactly the things that we drop when we go to the second column?
Exactly. So what you do is you can form the quotients between these, and because they have this order, these quotients, they will be always small. And the corrections from going to here, they will be of order y1 over y2. y2 over y1 maybe. Yeah, y2 over y1, right? Because y1 is the biggest one, so then it's downstairs, and so all of these ratios will be small, and you drop them. So that's the idea. Here you drop the corrections which go like exponentially in y, and here you drop the corrections which go with these things. So these are exponential polynomial corrections. Okay. I had a number of remarks. Some of these remarks I already said in words. So you can also read them in the notes, remarks. I can send the notes around if you like. So it needs an ordering. This I already stated here. And in fact, that's why one sometimes introduces these sectors which have these ordering included. Namely, these are the sectors where y1 over y2 is bigger than lambda, and y2 over y3 is bigger than lambda, and so on, and then yn is bigger than lambda. And then the idea would be that lambda in the strict asymptotic regime is large. That is strict. And if you want a picture, this picture is that, so this is remark number 1. Remark number 2 is that strict asymptotic, lambda is bigger, much bigger than 1, and F nil is F SL2 with these order corrections, order 1 over lambda corrections. And of course, the F SL2 can also be written now in the, not of course, but the idea is that this F SL2 can also be written in such a form. So it looks like a nilpotent orbit, and it is a nilpotent orbit, but it now uses these new ends, which actually commute. Well, they also commute, but the new ends in the SL2s which actually commute. That's the right statement. The old ends also will commute. Yeah, but now the whole SL2 commute. Okay. And with this ordering, with the strict asymptotic regime is now the following idea. If I plot absolute value of Z1 and Z2, then this is kind of 0. That's the 0 from both sides. Then I can go either close to this, or I can go close to this. And that is where these two SL2 orbits are valid. Yeah, in these two different orderings. So this would be R1, 2, and this would be R2, 1. So this corresponds to these two orderings, and then you can do this nice story. Now, comment number 3.
Sorry, one question. The picture that you are driving with this curved boundary means that really you want something which is tangent to the vertical line, or
no, I just mean that
just,
this is just this picture. It's just this condition which I'm drawing here. So this line here, it's just this condition, but this is a logarithmic transformation. That's why it's curved.
Okay, because logarithmic transformation.
It's always hard to draw these things because everything is at infinity. So it's okay. Now, as was already mentioned, there is a procedure, and now I get really sketchy. There is a procedure from going from this information, which defines the nilpotent orbit, to this information. So here I should warn you, this is not maths notation. Okay. So what is the idea? So there is a procedure where you can make out of these ends SL2s, which are commuting. So commuting SL2s, and these are satisfying SL2 commutation relations. And what is this F infinity? Well, this is actually the Hodge structure, a pure Hodge structure which lives on the boundary. It's a pure Hodge structure on the boundary, or associated to the boundary, and it can be constructed from this information, and in a rather non-trivial way. And in fact, you have to construct all of this at the same time.
But the old NIs are just the lowering there, or
No.
No. Okay, they get
Only one of them is the old one, and the other ones you have to modify.
to modify.
And it's really, someone told me that in physics there is a similar procedure. Right, the Born approximation. Born approximation.
Huh.
So where you really you try to start with something, then you check what doesn't commute, and then you try to get rid of this what doesn't commute, and then this is like an iterative procedure. Yeah, so it actually maybe exists in physics as well. I did have a look at the precise relation.
So tell us, you actually mean a pure Hodge structure and not just a Hodge flat.
Right.
So this is something like you take the Sl2 split thing at the origin, which is a mixed Hodge structure together with them.
Right.
And then you would take something like e to the I times the sum
Right.
to correct it in hats and apply that to this, and that gives you something in D.
So I have these formulas in my notes, but let me not go there. I will send them around just to save a little bit of time. So there is actually a pure Hodge structure which has a pure Hodge decomposition, and you can apply all the things which you know about pure Hodge structure, but it doesn't depend on T anymore. That's the important thing, because it really lives on the boundary. And in fact, what you can show is that this pure Hodge structure is compatible with these triples. And the way how to do it is pretty nice. So if you really don't like Hodge structures, then think of them now after all these.
Too late.
It's too late. Probably too late to come to this conclusion. But one way of doing this, and this is Matt, of course, alluded to this already. You can think of a Hodge decomposition also in terms of an operator which gives out of the PQ form, which spits out kind of an eigenvalue P minus P half omega. So you introduce an operator which on these individual pieces gives you a number. So that's what we like in physics, right? You want to attach a label, just a label to the space. These are all the spaces which have this charge. And that's why I call this operator Q at Chicotti. We have seen it in the Stoppard talk, calls this operator also Q. And what Matt did is he introduced this curly phi, and you write it as, I think it's 2 pi Q. And then what corresponds to this Q itself is then the derivative of this phi. Right? Okay, so this is just connecting to previous discussion. And the remarkable thing now is that this operator Q has very simple commutation relations with these triples. And it's constructed in such a way. What are these commutation relations? Yeah, I like this so much that I have to write it down. So. It's just very simple commutation relation. And what you then find is that if I now combine these ends into complex combinations, as follows, and like this, and L0 I like this. And I encourage you to sit down and do the computation. And what you will notice is that now L0I and Q infinity commute. with double M. They commute. So then we just go back to our quantum mechanics knowledge. If I have a number of commuting operators, it can write down the basis of states, now in physics notation. So if I give you a complex form, I can always assume, give this labels L1 to Ln, which are the spin labels under these individual SL2s, which are now complex SL2s. And then I can give it another label, which is the charge Q. So this is the eigenvalue under this Q infinity operator. So what does this mean? This means this charge Q is the PQ decomposition, and these labels L1 to Ln are the SL2 labels. And this labels all the states. We understand what this means. We can now use SL2 representation theory. We can, because everything commutes, you can show that these states are orthogonal to each other.
Sorry, what is this change of basis that you did in SL2? This must be an analogy in many systems in physics, no? Because like
I know what it is in mathematics. It's called the Cayley transform. Cayley transform. And in physics,
so for representation theory, I mean,
so in string theory, you would use these L's. That's why I call them L's.
Oh,
so this is like the complex SL2s.
Okay.
So in particular, what you find is that if you take the plus and the dagger, you get the minus.
It's like the Virasoro algebra.
It's like the Virasoro algebra. Well,
I mean, that's the level, no?
it's the level operator. So but there is another operator, and that's where Hodge theory comes from.
Yeah.
And this is Q. It's the charge. So now we translated this into a physical system, and you even don't need to think about vector spaces anymore.
So when you say Cayley transform, you mean what? Like in the period domain, or what is it?
No, with Cayley transform, I just mean this transformation from this real basis to this complex basis.
But in the R split limit setting, the Cayley transform is exactly pinging back and forth between boundary points and this sort of interior, for me, an interior point that you're calling the infinity. So applying Cayley transforms in all the directions associated to all the SL2s to get from your central point to get to this MP.
Right.
And it's the back and forth between the M's and the L's. That's precisely what Colleen and I are using.
I know.
I'm going to, yeah.
I know.
These classifications.
Is there an explanation of this pure Hodge structure in terms of the mixed Hodge structure of the singular of the degeneration?
Yes, yeah. So this information which I give here, it contains all the information about these about the mixed Hodge structures, at least when they are appropriately rotated. So you can reconstruct. Well, if you want, you just use these individual n's to then kind of take e to the minus n of this thing, and then you get the mixed Hodge structures from the individual spots in the SL2 split basis. So it's big. This is, I think, the most beautiful representation of this whole system at the boundary, and then you can use this representation to go in the strict asymptotic regime, construct your Sl2 orbit, and so on. Now, to wrap this up, the nice thing is when you go from here to here, you get even more information out. And these are these operators which Matt also introduced, which are these Lien operators. And in fact, you find n of them. So you always have to rotate in this new basis. And in each rotation step, you get information about the rotation matrix. And then this information is also on this side. And the amazing thing now is these two things are then equivalent. So if I give you this and this, you can also go back to the nilpotent orbit and reconstruct a complete nilpotent orbit. And this is the last remark, number 4. Ni plus minus n0 by fp infinity, and then these deltas can be used to get f nil back. And the Sl2 orbit theorem essentially states that these two things are equivalent. And that's the.
So can you give us some advance of what the deltas means in the physics
No.
system? No, no. Okay.
If you know, I would be very curious to know. So essentially, these deltas are, if you do the conjugation, you don't get quite the conjugate if you don't do it. So then Q doesn't go to, so the conjugate of Q, so Q infinity bar is minus Q infinity. Why? Because this was a property of this Hodge filtration, right? If you bar it, then you go, you just strip the indices, and this gets a minus sign. And this is only ensured if you do this with the right deltas, and this is violated. And this should kind of this rotation into a real plane, and that's why I call these things phase operators, because it's like a matrix phase. I don't understand what's the physical interpretation of this. I would be very curious to know. It would solve a lot of things which are.
I think maybe one nice example is that it rotates out the Euler characteristic correction at large complex structure.
Yeah.
Like it's an alpha prime correction, and this is precisely what this delta then removes to get to the Sl2 oscillation. So it does a very physical thing in that sense.
It does a very physical thing, but I don't exactly what the intuitive meaning of this.
What do you mean by remove? I mean, like you don't need to take it.
So in the Sl2 orbit,
Uh-huh.
the alpha prime correction is absent. Because, and you see why, because if I impose this hierarchy, then the alpha prime correction is higher suppressed compared to the leading correction. And that's what the deltas rotate out.
I see.
And then, of course, if you have multiple variables, they rotate much more out. They diagonalize the intersection numbers of the Calabi-Yau manifold, right? If you think about this, into Sl2 blocks. So they rotate out off-diagonal intersection numbers. So it's really cool. And since Damian spoke up, so Damian has a computer program where you put this information in, and you put this information in, and you press enter, I think. And then this information comes out, like then, all of them, and it's implementing the Sl2 orbit theorem.
But then they should encode the non-commutativity of the Sl2 blocks, or you don't think so?
Yeah, exactly. No, they do. They say how far the blocks are away from being commute. No, how large are the corrections from the general situation to these blocks, these non-off-diagonal corrections?
So the Euler characteristic is an example of how these blocks do not commute. I mean, not.
No, because the Euler characteristic is also there in a homodulous case, and then there is nothing to care about.
Okay.
But at the subsequent steps, yes.
Okay.
Yeah. It's like when you have intersection numbers, and then you have some off-diagonal intersection numbers, and you know already, oh, this modulus becomes very irrelevant if you go to the limit or this fraction. That's what this procedure tells you precisely how to do. Okay, very good. Now we went through this in quite some speed, but I think the nice thing is that it also tells you that you can decompose your real cohomology into eigenspaces of these Sl2s, and these are just the labels L0 I V. So this is nothing else than kind of what I wrote here already, right? So this is just, now you can decompose your space and give it, every form has now labels L, and these L labels, they correspond to the eigenvalues under this ni's, zeros, or under this L zeros. Yeah. Of course, you have to make sure to specify which ones you're talking about. If you want to decompose the real space, you take the n's. Okay, now finally, we should go in. Are we already over time now?
No.
Okay, so now let's, good. Now, how can we now use these things for the discussion of the distance conjecture and of the growth of the masses of our states?
Sorry, is Li the eigenvalue of n0 or of L0?
Yeah, so here in this, if you want them to commute with Q0, then you have to make them the eigenvalues of L0. But if you want to decompose the real space, you cannot use these complex operators.
Oh.
Yeah, so in this expression here, it's this, and in the upper expression, well, it's the same symbol, but it doesn't matter. It's what I write here. Now,
so Thomas, sorry. If you use the real ones, you are losing the information about the Q.
yes, absolutely. And if you look into the diagrams, if you look in these diagrams, which we've drawn multiple times now with the dots, the L information is on which line, on which diagonal line one is lying here. And of course, as I said before, this was the Hodge type. So like this was 2,0 and this was 2, for example. Yeah, and the L information just gives you the information where it lies here, but not if it is 0, 2 or 2, 0. And indeed, this is lost. But you can restore it in the small. Huh?
But you have multiple L's along all the different hyperplanes.
Exactly.
Combining all that information.
Now, what you actually now have to do is you have to draw all these diagrams next to each other, and then these L labels tell you where you are in each of these diagrams. So your form will have kind of information in each of these diagrams in this enhancement chain.
A mathematician would call this a multi-Lefschetz decomposition.
A multi-Lefschetz decomposition. Okay, very good. Now, how can we make now use of all of this? And what is one consequence from this is the so-called Gross theorem, which we used in our original papers a lot, and it's very easy to understand. So I want to give it, and it's essentially the statement: if I have an element in the following space, L prime smaller or equal to L, well, of L prime. Yeah. So if I have an element of this cohomology class with these labels being smaller than some L, yeah. So I put here an L, and then any state which has labels lower than this lies in this. And then one finds that the Hodge norm, so the norm divided with this thing, C, E, behaves like Y1, Y2, L1, Y2, Y3, L2, and so on, Yn, Ln, and then I drop the axiom, I drop the X dependence for simplicity, and then the norm at infinity. And of course, the norm at infinity is then where you replace the C with the C infinity. And what is C infinity? C infinity is nothing else than the Hodge the operator computed from this. Yeah, I gave you the rules how to get the operator C. And that's the theorem. So in other words, if I want to have a Q which falls off towards the boundary, I have to make sure that these L's are negative. Yeah, that it's really decaying towards the boundary. So in other words, if I have such a diagram, I want that for a Calabi-Yau threefold, for example, this would be 0, 3, 0, this 0, 3. I want to be, this would be the middle of the diagram. I want to be below the middle of the diagram. And all of these dots in the, which are below the middle will decay towards the boundary. And then the second thing I will just mention, Becker, Klingler, and Zimmermann gave recently a very nice refinement, which is quite remarkable if you think about this. Namely, they tell you that if I look at the off-diagonal parts, you even can neglect them in whole sectors. I can find a basis such that the off-diagonal parts are suppressed for all I, j. So there exists a basis. So this is really cool, and it's a very deep result actually. It really needs the Sl2 Orbit Theorem, and it essentially says that the diagonal, you can find a basis such that the diagonals are the ones which grow the fastest, and the off diagonals of this matrix are always suppressed. And so asymptotically, the diagonals play the important role. So many of the problems in string theory models and so on come from these ideas that you take the off diagonals in the metric and so on. So this just as a side, it's really nice to use, and I think we are just starting this. And all of these things is just on this R1, 2, on this sector, yeah. But lambda doesn't have to be large, so it's okay. And now let's apply this to our masses of the states. And what do we find? So the masses of the states were given by this formula, which I gave at the very beginning. And that's where everything started off. So this is truly general in the Calabi-Yau tree now. I have my Z of V, which was e to the k while Patterson divided 2 v wedge omega. And in fact, I can use Cauchy, and the masses are given by the absolute value of this. And in order that the distance conjecture is now satisfied, I want that if I go to the boundary, I want that this falls off like our coordinates y to some power a, where a is bigger than 0. So why does this imply the distance conjecture? Well, remember, I told you that the distance grows logarithmic in y. So if I plug this in, I find that this is then e to the minus a distance. Yeah. So now I have to select states V, which have a fall off in these y coordinates. But look at this. This is exactly what this theorem provides us, at least for the norm. And in fact, you can easily check that this is bounded by the norm of V by Cauchy-Schwarz. And therefore, you just need to check that each boundary one has a lattice or a vector space, a Q vector space with
Thomas, how are you normalizing omega? So this Cauchy-Schwarz.
Yeah.
it's normalized through this e to the k. That's the nice thing.
I see.
Because this is omega vet omega bar, and so this is 1 over omega vet.
In the Cauchy-Schwarz, then you must have like omega norm is 1%.
No, because the norm is divided out here. So then, so
Oh, I
e
see.
to
All right, got it.
yeah. So this Q vector spaces with L's smaller than 0. Yeah, sufficiently many L's smaller than 0. And if you have that, then you find that this decays towards the boundary, and you indeed find these states in these lattices or Q vector space because we rotate it, they become massless. Yeah, these would be asymptotically massless states. Okay. Now, now you can go through this whole classification and you can check in every case, which is at infinite distance, that such a lattice exists.
Sorry, all of them have to be 0. I mean, less than 0. This means the third component.
No, at least one of them.
Okay, at least one of them.
Yeah, at least one of them has to be smaller than 0. So they have to exist in I such that, and the other ones have to be 0 or smaller, equal to 0. Yeah,
And the physics.
I agree.
And the physics is different whether this guy is the first in your sequence or.
Yeah, it gives a whole hierarchy of how things become massless.
Gives you the A, no, the rate at which they
So
go.
it modifies the rate. Of course, I wrote this down just with one variable, but there's now a long power of things which decay. Yes.
Sorry to keep asking questions, but I mean, if you know that by the time you get to the origin and take all of the limits, so that your 3-0 form has moved, 4-0 form has moved, 3-0 is down to 3-1 or 3-2 or something like that, so that you're not in finite distance. Why can't you just, in the CKS framework, take the NI that does that to be the first in the sequence, so that NI remains rational? You know what I mean? So that we have a basis vector.
Yeah, it doesn't.
Q that will satisfy.
Yeah,
That's the obstruction. Why can't we just do this in this?
Maybe you can repeat the question for the recording.
Yeah. So why can we not just use the prove this in general and using these NIs? So yeah, it's not so, well. One important thing which I mentioned, you didn't mention it. You also have to make sure that Q, that this is unequal to 0. Right? So we don't want that this is actually 0 to leading order, because then we are killed. So you also have to satisfy this condition. And then you have to go to the individual diagrams and look at this, if this exists, and it always exists. And it's not, you see, now it doesn't, it's not anymore a very difficult problem. now it's not, you're absolutely right. There's no difficulty really anymore. If you know the machinery. Yeah, so then you just have to look at these diagrams and you will always find a lattice of dots which are below the diagonal, which decay off and have this property in every infinite distance. In finite distance limits, you will not find this.
So there's no conditions for the cycle to exist or the special Lagrangian to exist, or what?
And then exactly, and then the part 3 in the program. First of all, I have to say that there has to be an infinite tower of such states, and this is what we suggested. So this infinite tower, we suggested to construct this infinite tower by acting with e to the n to it. And then you can go through the various singularity types, and you see that in many of them, it generates an infinite tower, but in some others, it doesn't. And it's exactly where the dots are at the same level. So there's still a whole lattice, but the monodromy doesn't go between them because n always goes downstairs. And we originally didn't know what to deal with this, but I think now from the talk, from our discussion yesterday, I now understand that one can still generate them with monodromy. So that was already a very nice outcome. I don't know of the workshop and of our discussion yesterday that you can use the semi-simple monodromy to generate another decomposition, which is going in the diagram like this. It's very nice. Very nice. Anyway, so this was the original suggestion, and then you see that at most boundaries it works, but there are some subtle cases. There are some other cases where you have to do it, and this can be also now addressed with this framework. Okay, so this ends my discussion of the distance conjecture. So what you see is that all this machinery comes to life, and you can answer this very physical question in a very precise manner. Of course, what is an open question is whether there are actual special Lagrangians and whether they have stability, whether they are BPS states, whether they are sufficiently stable. And this machinery gets you a long way to check this, but we will not have time to discuss it. So what I wanted to...
Can you say a word of why do you need that? So why do you need the states represented by special Lagrangian?
Well, because we want to compute their masses with the central charge, and this is only true for BPS states, for such states. Yeah, that's one of the reasons. And the other reason is in the distance conjecture, these states have to be actual states which are relevant in the effective theory. They don't decay and are not just kind of multi-particle states, which just glue them together. So they have to be a new species. So there has to be a new state. And that's, if you have everything splitting into more and more particles, then this is not a valid answer to the conjecture. So they have to be really new particles. And this would be satisfied if they are individual BPS states. Okay, does that answer your question at least? Roughly, so this is kind of in the physics language what we mean by there is an infinite tower of states. We really mean different states, not just multiples of the other state.
So sorry, the physics meaning of that condition is what? So you said, but I lost it.
So the physics meaning of this is that it's coupled to the graviphoton, the state. So it has a graviphoton charge. That's the actual physics meaning. And it means that Z is in leading order, not zero. So the norm is always non-zero.
Yeah.
But it could be that it's just orthogonal.
Why do you need that it couples to graviphoton?
Oh, but if at leading order it is zero, then it's just an exponential decay. Then while this looks like as if it would be polynomial, this is an inequality, and this would be zero. That would fall off even faster.
Even faster. So in principle, it's okay for the.
Yeah, but this is more like field theory states. So this is like what you have in Seiberg-Witten theory. So in Seiberg-Witten theory, the states have this property. Well, Seiberg-Witten field theory doesn't have gravity, so the states are orthogonal with it. with respect to the gravity.
I see.
You want to have really gravity states.
Okay.
Mhm. So this is a condition. You have to find that each bounded states which talk to gravity and have this.
So in a rigid theory, everything would be zero. I mean, all
Exactly.
of this would be zero.
Exactly. So you can still have towers and so on,
Exactly. Yeah.
but these are not the towers which we are constructing. This is very important distinction. Okay. So now I asked before that I can maybe run a little bit over time, because what I didn't tell you is the answer to the finiteness conjecture. And I have a few more words on this, and this will tie in what Ben was discussing in his talk, in this lecture series. Right? I hope you are fine if we go a little bit over, since it's not open end, but
The lunch is delayed until 1 p.m. So
lunch is delayed until 1 p.m. That's very lucky that this happened. And so, yeah, please feel free to ask questions. So I will now want to move from the distance conjecture to the finiteness conjecture. The finiteness conjecture. And what I want to do the same with what I did with the distance conjecture. I want to take this very general, messy physics conjecture and translate it into a very concrete, provable mathematical statement. Yeah. The distance conjecture, by the way, we didn't really prove it completely because there were these loose ends at the end, right? Stability and so on. But this will be a statement which we actually proved. Yeah? Well, jointly with the mathematicians, I should say. Okay, so now let's why now do a Calabi-Yau fourfold. So from now on, everything is fourfold. And now you have to believe me that there is a string theory setting which has the following nice properties. So it's similar to the distance conjecture. You also have to believe me that there's this Z which measures masses of states. The mathematician and the physicist will know this following setting. Namely, in physics, we call F theory on Calabi-Yau fourfold. So F theory, this 12-dimensional theory on this Y, and we want to switch on fluxes. So what are fluxes? Fluxes are integral classes. So they just have another name in physics, but they are the same thing what Ben was talking about multiple times. They're just called fluxes. And these fluxes are integral classes of the fourth cohomology, and they pop out of string theory. And what do? They give an obstruction, really in the mathematical sense, to changing the complex structure. How do we see this in physics? In physics, we compute something which we call the scalar potential, which you can think of as an energy function. Yeah, so which measures the energy of the configuration, and the computation. So these sort of things I did when I was a PhD student. It's exciting to come back to this. So what you find is that the energy function which you find is the scalar potential is this Q, this polarization, then this G4, which is the integral class. I use the physics notation now, do not get confused. So physicists like to put indices which indicate something, right? This just means that it's a four-form. Yeah? There's the while operator. And then there's another piece which is this. And there's a coefficient C, which we will not care about. This kind, oh, well, C is not a good letter. A. There's a coefficient A, which we will not care about.
So what is this B? This B quantity?
The scalar potential.
It's kind of, okay.
This B.
Yeah.
Yeah. So this is it's a real function on the moduli space, because this depends on the moduli space. So this is really depending on the moduli space. And it becomes, depending on where you are in the moduli space, it becomes large or small. Yeah. But notice that it's positive definite. Right? It's actually a positive definite function. So it's always bigger or equal to 0. And what we want in physics, we want to look at vacua, which means minima of this potential. And the global minima of this potential, well, this is now hardcore, is just when this is equal to this. Okay, that is just 0, and since it's positive definite, that these are the global minima. The global minima are when C on G4 is equal to G4. Now let's quickly check when this happens. So when does this happen? Now we know everything, right? We know how C acts on the PQ decompositions. So we decompose our integral class into PQ forms, and we realize that if G4 is an element of H2, 2, in fact, of the primitive part, I mentioned this in the first lecture, but don't worry too much about it. If this is 2, 2, this is satisfied. Okay. But now you have an integral class, which is a PP form. Yeah, so this was an integral class. I changed notation to be quicker, which is PP. Oh, but that's what Ben and also Matt told us are Hodge classes. So fluxes which satisfy this condition, and as a special case with being PP, 2, 2, Hodge classes. That's not the most generous situation which you can have. You can also have G4 being in the 4, 0 piece plus 2 piece plus 0, 4 piece. And then this is what we call a self-dual class. Okay. Now we are there. You can use the theorem which was discussed in Ben's lecture to discuss the first case. And it gets even more amazing for the mathematicians. For the physicists, there is something coming which you already know. Namely, in physics, we actually think of G4, which G4 as a charge on a compact manifold. So we have our manifold, our Y, and we think of this G4 wedge G4 as giving some plus charges here, some minus charges here, some plus charges. Yeah, depending on if this is positive or negative, you can think of this roughly like this. And consistency by Gauss law is that all charges have to cancel. Now there are some charges which come from the curvature of this manifold, which I don't know how to draw. Curvature, and they give some charge. And so in physics, we know that there is a consistency condition which states that this has to be the Euler number of the Calabi-Yau fourfold divided by 24. It comes from the string theory setting. And this is called Cancellation. think this is important maybe for mathematicians because you read this in our papers and then you maybe don't know what is the relation, but this is nothing else that the self, how did Ben call it? The self intersection of the integral class is bounded.
Yeah, so maybe smaller or equal, no?
Yeah, in fact, there is a bound because there may be D3 grades more.
Exactly. Yeah, exactly. So you can even have D3 and then it's just bounded.
Yeah.
So for us, it's enough that it's G4, that G4 is just bounded by some K. Some integer. Okay. That's precisely what was part of this theorem. And then there is this famous theorem of Catani, Kaplan, and Schmidt. No. Of Catani, Lien, and Kaplan, which was discussed in Ben's lecture. And actually, he gave us a proof of the theorem, a reproof of the theorem using tame geometry. Well, Ben was not part of the team. He discussed this there. Okay. And what they showed is that actually the loci in the moduli space, where these Hodge classes satisfy this condition, they show that there are finitely many such loci. Finitely many loci for property 1. If the Tadpole condition is satisfied. What is this Tadpole condition? It's this condition. Tadpole condition star is satisfied. It's a theorem. The theorem is even more remarkable. Even though this falls out from this tameness so easily, well, after using these heavy theorems in some sense, it's not only finitely many loci, it's or finitely many possibilities. Yeah. So there are finitely many combinations of loci S inside the moduli space and fluxes, choices, yeah, finitely many choices. They also show that it's algebraic. In fact, this is very remarkable. So you have to imagine if any one of you has kind of computed periods, these are horrible things, right? Like even for the simplest examples, hypergeometric functions and all of these things. But the loci at which this fluxes, this G4, these integral classes satisfy these conditions, they are just given by polynomial equations. So all these exponential corrections somehow.
But is this connected to the, there was a few years ago the connection between flux equations or attractor equations, flux, vacua, arithmetics, in some lectures of Moore and
yes. It's not directly. I don't think he discusses this connection in very much detail. If I don't remember this. No, I don't think he does. But it's, of course, it's all related to this. It's all in the same ballpark. So the attractor equations, they don't fit quite in this framework, but what I'm going to say next, they fit better into what I'm going to say. So this is
yes, a question just to see if I understand. So
sure, please.
If you fix the flux G4, then you're saying that if I look at the locus in the moduli space where this Tadpole condition is satisfied, then it has finally many connected components. Is that what you're saying?
No, almost. So if you fix the flux G4, you have to fix, this doesn't depend on the moduli space. So you just fix a flux G4 which satisfies this condition. And then the locus in the moduli space, which corresponds to this, has finitely many components, okay? But the theorem is deeper than this. It says that there are only finitely many pairs. So there exists only finitely many G4s which you can pick to satisfy these bounds. And the collection of all of these loci is algebraic, or all of these loci are algebraic. Algebraic finiteness is fixed anyway. So if you say something is algebraic, it's just given by finitely many equations. But I wanted to highlight finiteness.
And there is no statement about the dimension of the loci.
You can imagine what we spent the last half a year thinking about. And even discussing with the mathematicians, I sent to Ben the tadpole conjecture, which says something about dimension about this loci. I tried to translate it into mathematics, but it's so far.
This is maybe moving away from the setup, but how does this fail in other setups in which you have these fluxes that doesn't enter into the tadpole, as you can have, the dilute flux and all that?
Yes, yes. That's a good question. It fails in the sense that if you would brute force translate what you want to do into this setting, these fluxes, they would be not self-dual. In fact, what you can have is that they have a little bit of violation of self-duality. You can even arrange it such that they kind of fall off towards the boundary. That's exactly what happens in this type 2A settings. But you violate the self-duality condition. And then finiteness is not anymore guaranteed. So self-duality is very important for finiteness, and 2-2 is also very important for finiteness, which is weaker than this one. This is weaker than this. But it's a very good question which you're asking. And that's why my feeling is that if one wants to look in this type 2A setting, well, I don't want to start fights, that maybe it's some sort of back reaction effect. This doesn't belong in this discussion here. This is all very understood and clean. Okay, very good. And then in the last 10 minutes, I just want to quote, because the nice thing is that we heard already that this theorem can now be proved using the definability of the period map. This we have seen in Ben's talk, right? So you use the tameness of this period map, which I briefly recalled before. You use the tameness of the period map, and then the fact that these loci, these two loci, Ben explained this, but maybe this was very brief. That these are actually in one of these filtrations, yeah, namely in this case in the F2 filtration. So this is holomorphic. And then he used holomorphicity together with definability in our physics language to show algebraicity. Yeah. And now let's go to the more general case. And this is this new theorem, which is a generalization of this finiteness part of this theorem. And this is, and I will just state it and maybe give one.
Sorry, in the statement of this finiteness theorem, are you are you allowing to change topology via conical constant or something like this or not?
No,
No.
or for a fixed y. Yeah. Finitely many, so yes, I divide fixed y. Well, they don't do, of course, they don't do it for geometric families. They just do it abstractly in variations of Hodge structure. Yeah, but you're not allowed to change the Hodge numbers if you want, right? Otherwise, you show that there are only finitely many Calabi-Yau manifolds. Okay. So now what is the? So I'm almost at the end. That's very good. So this is this new theorem. And it essentially states that indeed this finiteness conjecture, if you fix the Calabi-Yau manifold, is satisfied in this setting. So if you take L bigger than 0, integer, and when you find that the locus of self-dual classes X, V element E. So E is the Hodge bundle. What is the Hodge bundle? The Hodge bundle is just the vibrations of the PQ spaces over the base, over the moduli space. Yeah, this as a bundle. And we have heard a lot of discussion about the properties of this bundle. It's the Hodge bundle. But I want to state the theorem in a precise way, so that allow me to write it like this. Then any element inside this, which has the property that Q of V, V is equal to L. So now we have the locus of self-dual classes, namely all combinations of points in the base, points in the moduli space, and fluxes. These are the fluxes, the V's. This locus is, sorry, there's a mistake in my notes, is definable in R X and
But self-dual was in H40 to 2 and 04. And here you are putting HDD only. So
yeah, you're right. Sorry. Yeah, sorry. Problem is I copied twice the Lien theorem in my notes, which is completely stupid, of course. I have to correct this in my notes. So if you have my notes, please don't.
Wait for a correction.
Yeah, please wait for a correction. Like this. Yeah. So all the self-dual classes, which are integral, satisfy self-duality and have this Tadpole condition, give this locus is definable and therefore finite, because that was one of the theorems of Ben, right? He said that it has only finitely many connected components, so there are only finitely many fluxes possible, because fluxes are discrete. So there is no connection between the fluxes, so there can only be finitely many fluxes. Okay.
So, but then this theorem is for an arbitrary variation of Hodge status, nothing to do with the Calabi-Yau. So it's completely general.
Yeah. So it's really a generalization of this very general theorem. Yeah. But it's not, we are not quite there where this theorem is. Namely, it also proves algebraic, and we have a much weaker condition here, which is just definable. And why? Because holomorphicity cannot be used anymore. because if you look at this is not in a holomorphic. So this is not anymore in a holomorphic F. So actually, this is and the restriction of P is the map from the Hodge bundle to the moduli space M has finite fibers. Which also follows from definability. And finite fibers means that because of definability, there is a bound on the number of vacua in each fiber. Yeah. Okay. So this is the theorem. I should say by whom, yeah. So this is by Bakker.
By P from E to M, you mean P from that big expression, not all P.
Say again.
P is going from the stuff it braces to M. That's what has finite fibers.
Right. Yes.
Yeah. So maybe it should be curly E.
Yeah.
Curly E equals that big set.
Oh, yeah. The restriction of P. Yeah. Sorry. To the Sl2 locus. Yeah. Has finite fibers. So I wanted to write it down properly, and I didn't copy it right. And then Christian Schnell and Zimmermann, Jakob Zimmermann. Okay. And I will not give the full proof, obviously. It actually uses it uses much of what was said in Ben's talk, actually. These theorems were all used, and the most important piece which was used is the definability of the period length. And why is this so remarkable? It's actually a theorem where holomorphicity is not central to the story. So it's actually highlighting very much so that this tameness exists in the world over the real numbers. Because you cannot prove this theorem when you try to talk about holomorphic things. So it actually nails the realness of this whole tame geometry. So it shows the power of these statements and how deep these statements are about tameness. And I don't want to give the proof, but I want to give you one thing from the proof which I find very exciting, and maybe you use this in something. There is a very nice result which we use. It is, for example, can be found in a book by Knese. You might wonder, why is the tadpole condition important in this theorem? So why is this condition important? And in fact, it is this condition which gives you the reduction, or it is this condition which gives you an important finiteness reduction. If you leave out this condition, it's not anymore true, this theorem. Yeah, likely. The proof doesn't work. And why? There is a nice result by Knese which says the following. If you want to generate your full lattice of fluxes, so this was this full space H, Z, the integer, like the integer flux lattice, you cannot generate this by starting with finitely many fluxes and acting with. So the idea could be, I take a flux F, so an integral class, and I act with my group GZ on it. So the GZ is the group which I introduced at the beginning of these two lectures, but over the integers. So I take an integral class and I rotate it with integral matrices. How many integral classes do I need in order to generate the full lattice? Infinitely many, actually. Right? So, however, the theorem by Kneser says that if I demand that Q of V, comma V is L, then only finitely many orbits needed. So in other words, you can start with finitely many integral classes, and you rotate them with your symmetry group with the G over the integers, and you can generate all fluxes which satisfy these conditions. And then what we do is we just have finitely many orbits where we have to check that the theorem is that this is true. So we split up the lattice into finitely many orbits, and then we prove finiteness along each orbit. So this tadpole condition, which comes from gravity, gives a very important finiteness reduction.
So physical, is there any physical meaning for this GZ and the way you generate this?
Yeah, so it's no.
Yeah, that's okay.
But the important thing is, this is very important, and that's why I also was stressing this in Ben's talk. This is not true if you use the monodromy group. So if you would do if you take the monodromy group in general, and you would act on this, you don't generate the full lattice. And the monodromy group has a physical meaning, right? It's kind of the gauged global symmetry group, which you have to divide out. But this one, it's just orbits of this very general base. It's kind of base changes in the integral over the integers. But so it's very remarkable because you need actually the definability of the period map modulo the whole this whole group, not just the monodromy group. The theorem would be wrong if it were only with respect to the monodromy group. Or not wrong, but you could not prove it like this.
Does it need to have the full thing, or can it be in between?
This I don't know. Yes. But I know that if you just take the monodromy group alone, that's not true. I don't know what is kind of the minimal assumption that you have to take. So this is true. Yeah. But I don't know what if there's something we could. Yes.
So I'm a little confused about this statement. We need finitely many VIs such that the orbits GZ and VI cover what?
The whole lattice will satisfy these.
But the set of V's that satisfy Q of VV equals L is finite.
No, this is not a positive definite form.
Oh, I see. Yes.
So
I have one other question.
Sure.
What does this say, if anything, about you proved a nice theorem about finiteness of this map, but what about its image? In other words, the image of the restriction of P to the thing in braces. So it's not a countable union or finite union of anything inside it.
No, it's definable. The whole set is definable. So
it's image and image definable. That's what you're saying.
Yeah. Very good. That's the end.
Just one specific question. What is the analog of this tadpole condition for the theoretic string? Is there, I don't know.
Well, then you end up, you first have to set up the whole thing in the heterotic string, and then there are not as many fluxes at your disposal, and then the story changes completely. They're also, the heterotic story is a very different story. Is that fair to say? It's not easy to change this to the heterotic. Of course, if you have a duality, then this G4 fluxes, they map into non-trivial bundle configuration on the other side.
But there is an interplay between the curvature and the term classes of your bundles.
Yeah.
You need to satisfy, and that will be the tadpole.
Yeah.
The number of NH5 parameters you can have, but there is a number. But if it
But it's like
plays
the
the same role as in here, that's not good.
You take the identity with NH5, right?
Bianchi identity.
Yeah, so
Those are Bianchi identities.
Yeah.
Like integral versions of them.
Okay. Yeah. So the problem is, or the nice thing is that the Bianchi identity here is a scalar condition, while in many of the other dual settings, it's actually a condition in cohomology. So it's not as simple as this is the cleanest version of such a setting. But there exist all kinds of dual situations. For example, the type 2A setting, there's also a tadpole cancellation condition, but then it's a condition in cohomology, which you can integrate over all possible basis elements, and then you get many conditions. Yeah.
But I think that some of the ingredients in here, like self-duality, also appears in dual settings.
Sure, of course,
even in generalized geometry,
Everything,
complexifications, you get the same thing. So like
You can
this could be applied to other settings as well.
absolutely. You just have, yeah, absolutely.
One question, anyone?
Everyone is hungry. Sorry for.
So let's thank.